new here. I think last time I was here in 2016. So yeah, so I'm going to tell you about some work that I've been doing with Brunei for many years. I can't write anything here, right?
Yeah, you can write.
Only here. So yeah, so the title, as Pushkar said, is massive. Okay, I will change it a little bit. Massive S matrix from positive geometry or from positives. But I won't. So I won't assume that people are familiar with the subject because it's relatively new. So I will really spend a lot of time introducing the basic ideas, and hopefully we'll have some time to. I'll get some time to tell you what we have been doing recently. So part of this, I mean, this all the work is in collaboration with Brunei. And who is at Caltech now, and part of it we came out last year, and some of it hopefully will appear soon. Okay, so let me first start by giving some basic motivation to the whole subject. So the sort of the main emphasis of this program is to answer the following question, which is that what are the class of functions of momenta, Kn momenta, so it's P1 to Pn, which correspond to unitary and local or causal S matrix. So when I write it like this, maybe I change the notation. Maybe I will write it like this. What I mean is that usually we have the S matrix, which has the momentum conserving factor. So that I'm kind of stripping out always in this notation, and whatever else we get is what is usually called the reduced amplitude is what we are going to focus on. And the main kind of ultimate question we want to ask is that what are the, if I give you any function of momenta P1 to Pn, which are of course on shell because computing amplitude, so Pi square, Mi square, then how do I know I gave you some function? How do I know that this function is indeed a S matrix of some physical theory? And this answer to this question is not at all obvious. So for example, if I just told you that if I consider a 4-point amplitude, even 3 level, just even 3 level answer is not obvious, because if I just wrote a function like this, okay, I mean, yeah, if you look at this function, it looks like this itself is not an amplitude of any theory because we are using the U channel. But it turns out indeed this is actually a 4-point amplitude if your particles have color. So if your particles have color degrees of freedom, then you can compute, and let's say the color indices are A1 to A4. Then if the ordering of the particle is fixed, so when we do color, when we have colors ordered in a particular way, then we fix the ordering of the particles on a circle. And then that means that the only diagrams we can draw are those which are the diagrams we can draw here on the plane. So we have only 2 diagrams, this and this one. And so, as you can see, this is the S channel and the P channel. So, this is indeed a 3-level amplitude for a color ordered theory, where particles of color. Another extreme example is larger. So not large than, you just have color. So yeah, so any amplitude. So if you look at full amplitude, a 3-level of course for this theory, and you have color, then in general you can write this as some over all possible commutations over 4 labels, and you just remove the cyclic commutation, and then you have the color color tensors. So if you have some particles in the adjoint, then you have this, and then you have the this ordered. So maybe I should change the node. Let me just call this one. So I fix some commutation. Sorry. and then I have a amplitude which is sigma 1, sigma 4. So when I write it like this, I mean that I fix ordering and then account for all the channels which can be drawn with this ordering phase. So if the ordering is just unit permutation, so this is the full amplitude for any color group, and I mean we are not doing a large n function.
But why can't we draw the U channel?
Because it's not for this ordering, it never occurs, right? So if for this ordering, so if I take sigma to be identity, then so that term is simply A4 1 2 3 4. Then there is no U channel that we can draw with this ordering fixed. Because we are saying that two particles came with colors, T1, TA1 and TA2, they collided. So only the adjacent colors are getting contacted with each other. So when we do a color division like this, but it's a definite, I mean, that's the result that comes out. That this particular contribution, which is called color order contribution, is all the channels which are consistent with this ordering. If you just draw the, if you draw the, so if one way to understand this is that if you have the structure constant, right? So I mean, this thing came because we have the structure constants which are also accompanying the vertices. So the U channel structure constant is when you think like F, A1, A3, B, FB, A2, A4, and this thing can be written by using Jacobi, etc., as some single trace. And that single trace will only come from ordering which will have 1, 3, 2, 4 ordering. So the ordering which is 1, 2, 3, 4 will only have A1, A2 or A2, A3 in the structure constant.
Okay.
That one.
Yeah.
So and there's another extreme, more extreme example which is in the Young-Mills case, again tree level. So if we consider 6-point amplitudes with say 3 helicity gluons negative and 3 positive. So this is called NMHV amplitude. And
sorry, Alok,
no, the what is observable is this thing, the full amplitude. But the point is that the full amplitude can be written as a sum over the color order amplitude. So you are right that, but you see that the U channel will come with a different color structure. So the thing is not, I mean, it is this times some, I mean, if I was suppressing color here, but it's really lambda for the 1, 2, 3, 4 ordering. Then I've observed the structure constant plus lambda for 2, 1, 3, 4 ordering. Then you have 1 by T plus 1 by U, and the third one. So they never mix. Yeah.
So for abelian case also with 5 bars, if you have a neutral particle that can mediate, then only S and T channel.
Well, abelian case, but I guess all of this will collapse into like a single coupling. So they will all combine at the end of the day. I guess that's what you're asking.
No, I mean for abelian case when you have 5 and 5 bar.
Yeah, if your external particles are charged.
Yes.
Yeah. And if your interaction with 5 bar, then of course, you have 5. If this was 5 exactly, 5 bar, 5 bar. Then you only have.
If you only have neutral particles in the theory.
Yeah. Then you only have S and the T. Okay, then you don't even have the U channel. So that's probably a simple example. Thank you. Yeah. Okay, good. So that's a simpler example that if I just give you a function, you wouldn't know whether it's an S matrix theory. And then another extreme example is if you take this tree-level amplitude for 6 gluons where the helicities are split, and as some of you may know, it's most convenient to write this in terms of what are called spinor helicity variables. So for the purpose of talk, not very important if you don't know, roughly speaking, any massless momentum P mu can always be decomposed into sort of the spinor. So we can write it first of all in terms of the SL2C indices, and this can be decomposed into like dotted and the undotted spinor. Okay, so this is the notation of the spinor helicity, and it turns out that if we compute this, and the most efficient way to compute this is using what is called BCFW recursion relation, which is a a little bit not, strange technique in the sense that the computation itself doesn't respect locality of the Lagrangian, unlike the Feynman diagram it takes. And so if you compute it, you get an answer which looks a bit strange. So there is some stuff here that some function of, when I like this P1 to P6, and also polarization epsilon 1 to epsilon 6. And then you get a pole which looks very weird. It looks like 4. So this notation I will explain completely. 2 plus 3, 5. And this notation means we have 4, 2, 2, 5 plus 4, 3, 3, 5. And in terms of this, it simply means we have lambda 4. This means we have this notation simply means we have epsilon AB lambda 4A lambda 2. And this means for the same thing for the dotted indices. Now, if you look at this thing, it looks very, very strange because this looks like some non-local pole in the theory. Because it's not a pole which is like 1 by S or 1 by T. It's like you're adding 2 momenta, 2 particles, and it's like a pole which roughly speaking looks like some Pi plus Pj kind of pole, which is a bit strange. Pi plus Pj square kind of pole, but when ing are not consecutive to each other or anything like that. So if you do a Lagrangian computation of this, you will never see this particular. You will not have a form like this where a pole has this kind of structure. So it looks a bit strange, but it turns out that if you compute residue of, so there are many poles here, and those are the poles that you get from the Lagrangian perspective. But if you compute residue of this pole, it turns out that it's actually 0. So if you evaluate this function at the pole coming from here, it turns out that the residue, so at this pole, that is 0. So it's a fake pole, which is consistent with the idea of locality. But if someone just gave you this function and asked, okay, is this a S matrix for a local theory? Then you would initially, if you didn't know all this, you would say no, because it's not local. So
by Lagrangian poles, you mean poles corresponding to intermediate particles unity
on shell. Yes. So these are 2 examples already at 3 level which tell you that answering this question that we give you some function of external momenta, and if you have spin polarization, and asking whether this is a function corresponding to S matrix of some theory is a non-trivial question, and that's the question with which this program that we will try to discuss a little bit was sort of, that's the main motivation behind this program, as to what are the class of functions that quantify as S matrix of some theory.
So, Alok,
yeah.
Ti plus Pj whole square kind of quantity can appear if there is something.
But if ing are not successive, right? If you have a Yang-Mills theory, then if you are looking at, you only have, as you know, the cubic contribution in the pole, and if you have, so if you're looking at ordered amplitude, like this is the ordering we have chosen, then you will not get, if P2 plus P4 square will not get. Yeah. And so partly
in the Lagrangian language,
yeah,
momentum and polarization language,
yeah,
what this pole looks like?
No, you will not see it.
You will not see.
You will never see it. If you did the Feynman diagram computation, which actually you cannot do for this because it has some, I don't know. It has 10 to the 5 ordered number of terms in Feynman diagram. So, but if you do it, you can show that this pole is not present.
I see.
Yeah. So in fact, this is one of the mysteries of the recursion in general. These are called spurious poles. And even though for this class of amplitudes, we know that, there is a deeper understanding, part of which we will see today, as to why these poles don't contribute. In general, if you do like a generic Yang-Mills amplitude, it will also get these poles. And there is no, as far as I understand, a concrete understanding of why they cancel. And actually, it was the cancellation of this pole that it was the first paper by Andrew Hodges in 2009. It's called Spurious Poles. I think an MHV amplitudes or something. Because it, and I just schematically I'm telling what he did. So what he said is that we can think of what he realized rather remarkably is that this amplitude can be thought of as it is very, very schematic. Sorry, like this amplitude is equal to volume of a specific polytope But this polytope is sitting in a very like auxiliary space, which is called momentum twister space. And once he shows this is remarkable in the sense that, so when we compute volume of a polytope, like for example, if we have a sum, then one convenient way is to break it into smaller chunks whose volumes are easy to compute. But when we do that, we kind of introduce some fiduciary inner surfaces, and it is this inner surface. So he said that doing BCFW is equivalent to breaking this into chunks and computing volume, and we break it. That means we are introducing extra fake boundaries, and which are not there in the final when we sum it, and they correspond to the spurious poles in this case. But this was the first paper which kind of showed the promise that maybe this kind of geometric meaning would be very useful to understand estimative theory. So
BCFW is not like going to one particular phase of it and then again to some phase and so on.
No, BCFW is really computing 6 point from 3 point. And so it's like really computing from smaller chunks of the volume in that sense. So it's really like, yeah, it's point by point rather than from pole by pole. This is the final answer. This is the final answer, which has a lot of. There are no the full term is proportional to this, but this is itself has sum. I mean, I didn't write this. This is sum of actually I think 2 terms, and so the residue of term 1 on this pole is minus the residue. Yeah. This is the final answer. This is yeah. I mean, we can take. There is more technicality. This is one spot. By the way, the another ambiguity here is that this is not even unique. Like this is the answer. If you know BCFW, if you did recursion in momenta 2 and 3, but if you did in like 3 and 4, you will get a different representation, which will have a different spurious pole. So but in the end, even for that, residue is 0.
So you are saying BCFW sum has this technique for 5 options.
No, not BCFW. I'm saying if you did Feynman diagrammatic, which will have like huge number of terms, two terms to compute, because they have structure constants, you have to contract, etc. But BCFW, this is like less than a page computation. But any representation will have Fourier pole in BCFW. For this amplitude, there is no representation in BCFW which has most Fourier pole.
But is there a general that space pole will cancel, or you have to like check it?
To my understanding, for generic Young mills, I am not aware of any proof of this type. Yeah, it is only for this NMHV where you have 3 minus and everything else plus. So if you have MHV, no spurious poles arise in BCFW. And the first time you see spurious poles, if you have MHV is 2 minus.
Right.
If you have 3 minus, you start seeing spurious pole, and there is a proof by Hodges. I am not sure of any proof beyond.
But it is for all MHV.
For all endpoints, yeah.
Any
endpoint, yeah. So his remarkable thing is for any endpoint.
What is MHV?
Sorry, next to MHV. So MHV is the like the maximal helicity viability, and this is yeah. Okay. So now the sort of one perspective on this question of what are the class of functions that qualify as matrix came from some of the worldsheet formulation of one of new theory. Which also is known as the CHY formula, where this is name of the physicists who discovered it. So I mean, again, I won't go too much into details, but just tell you what their perspective is, which sort of at least conceptually will play an important role in our discussion also. And there, the idea is that let's not think of amplitude coming as some functions in the space of momentum, but what they, because it was inspired by the worldsheet formulation of string amplitude, and the point is that let us consider, instead of this, so instead of looking at the momentum space, or spinor elasticity space, space P1 to Pn. I mean, as the space in which we want to evaluate amplitude, let us consider the auxiliary space, which is basically the string worldsheet. So it will it's the moduli space of n punctured Riemann sphere. So it looks a bit ridiculous. I mean, this seems like it may not have anything with the FT amplitude. And the idea is that, so roughly speaking, what this is simply you take n points on the sphere, sigma 1 to sigma n, and then you quotient it by SL2C action, where each sigma a goes to, that is, you just, this is the gauge redundancy where each sigma a goes to a sigma a plus b by c sigma a plus b, where this is just the SL2C. And so what they showed is that, so of course this space string theorists have understood very well, and they understand how to define measure on this space, etc. SL2C invariant measure, etc. And roughly speaking, the CHY formula was that if I want to compute, say, n-point amplitude of a theory. So let me first, so most of the work in CHY, and this will be important for us, is where these are massless particles. So there is some work if these particles are massive, but it's not nearly as developed as the particles. All the particles are massless. So let's just, for the sake of explanation, stick to massless particles for now. And the statement was that if you want to compute this, all you have to do is do of integration over this moduli space. And so there is a SL2C invariant measure, just coming from old string theory amplitude computation, which is universal, theory independent. So this is something which is just something that is fixed by SL2C invariant. So we don't, that doesn't depend on any physics in that sense. And then the important part is that the sort of the information about the momenta is contained in what is called scattering equation. So you have to, so yeah, let me rewrite it. So you want to integrate any function of n punctures and n momenta. So given any function, you want to integrate it, but you don't want to integrate it over generically, but you want to only sort of localize it on what are called scattering equations, which are, I will just write it in the next bit. So I'm going to slightly modify this, so let me first explain and then slowly sort of modify it. So the idea is the following, that you want to look at the location of these punctures is dictated by solution to what are called scattering equations, which are equations that, these are our usual Mandelstam variables, Pi dot Pj. So these equations are basically, you sum over all, for each I, you have one equation. And so you sum over, you take these equations and you solve them from sigma. And those solutions, you plug it into some function. And the statement is that, which I will say that if this function satisfies a very simple property, then you will get S matrix of some theory of massless particle. So analyzing this, so our question kind of transmuted into analyzing these this class of functions. And what they showed is that because you want SL2C invariance, the only constraint on this is that it should have SL2C weight plus 4.
So, Alok,
yes.
As a result of this delta function, the integral will be less dimensional, right? Not the full modular space.
I mean, it will be localized on the solution of the
localized?
Just localized.
Point life.
Yeah. And so SL2C weight, because you want the whole thing to be SL2C invariant, because this guy doesn't know anything about any SL2C, that's a fake redundancy. So, and this is SL2C invariant, this has some SL2C weight. We can easily check that under this transformation, this is SL2C weight minus 4. And so for the whole thing to be invariant, this should have SL2C weight plus.
Sigma j, what is the range? Is it like 9 minutes?
I'm explaining this now. This will be important for us. So there is some, let me explain this. Yeah. So this is what the scattering equations are. Let me write them a little bit more. So this, this equation basically is, so let's take an example. Let's take n equal to 4. And so in n equal to 4, let's take I equal to 1. So we have a equation, and let me take I equal to 2, you see why I'm okay. So we will have equation which is S12 by sigma 12 plus S32 by sigma 32 plus S42 by sigma 42 equal to 0. The reason sigma 22 didn't come is because S22 is 0. And sigma ij is simply sigma j minus sigma I. just a shorthand notation. So these are the equation. But now what happens is that because we have SL2C redundancy, we can fix 3 of these functions. And so the fixing usually, I mean, for example, we could take sigma 1 to be 0, sigma 3 at 1, and sigma 4 at infinity. And so then this term drops because sigma 4 went away, it goes to infinity. And so we have, but we have fixed 3 punctures. So to begin with, we have 4 equations, right? We have n equal to 4. We have 4 equations, but now we have fixed 3, so we have only 1 equation. So in the end, so this thing actually has only product is only over n minus 3. And it's typically denoted as it's prime to say that there will be product n minus 3. So yeah, even here, basically sigma 1, sigma n minus, I mean, 3 of them are fixed, and then you evaluate this integral. And so then this seems quite remarkable that, I mean, we can think of this as an n minus 3 form. Because you can easily, I mean, because this is an n minus 3 dimensional, because we take any punctures and quotient by SL2C, so the dimension of this space is complex dimension n minus 3. And so we are really integrating a n minus 3 form. So the CHY kind of gives a partial answer to our question. That you give me a n minus 3 form of SL2C weight 4. And if I evaluate it on the solution of scattering equation, which are completely theory independent, these are universal. So that should give me principal S matrix of some theory. And so the only thing is it's like Lego. I mean, you can now start playing around and build ions, and people started seeing that you can get all kinds of nice theories, Einstein-Young-Mills and Young-Mills plus phi cube, and some of the more surprising theories that came out are Galilean theories, etc. People build this. So that's the unitarity of the amplitude. Oh, that's an excellent question. So yeah. So now we can ask the following question: that where is the information about unitarity in this, and even locality in some sense? Like this is a differential form or function on this auxiliary space, and it turns out that both the unitarity and locality are really obtained by understanding the geometry of this moduli space. So what happens is that if these two punctures coalesce, then this moduli space kind of breaks into 2 low dimensional moduli spaces. And it turns out that breaking, I mean, we will see this in more detail in a simpler way, gives us locality. And the fact that the unitarity is a little tricky in the sense that these functions, if they have simple poles in sigma m and sigma j, then that will give you local amplitude. So that's also, if you want tree-level amplitudes, then yeah, so that you may have to look at like specific functions which are like simple poles, etc. But yeah, but we will see this in much more easier way. So, but roughly speaking, that was the answer. That if you want to look at integrants of SL2C weight 4, and you can just start playing around. You don't have to even assume simple pole. You just see what kind of theories you get. That was the. But one disadvantage of this is that it's one, it is in auxiliary space, and 2, that to my understanding, most of the progress has sort of been done for massless particles. So if we ask, okay, can we obtain an ion for, suppose I give you a Lagrangian, which is function of 2 fields, which has dou mu phi I equal to 1 to 2, and then let's say minus mi square phi I square, and then let's say we had minus lambda 1 phi 1 cube, lambda 2 phi 2 cube, and lambda 3, let's say phi 1 square phi 2, some Lagrangian like this. And you can ask, okay, have people discovered any ion which gives us even tree-level amplitude? And so far, as far as I understand this, there has not been that progress when you have multiple fields with different masses. So as far as massless particles are concerned, this gives us a lot of functions which give us tree-level amplitude, a lot of forms actually on this M0 space, but then there is some limitation. Right? And another disadvantage of this formulation is that if I were massless, but say quartic or higher order interaction. So if I take a Lagrangian for suppose we have massless scalar field, so we have like just say dou mu phi, and then minus lambda phi 4. And then it turns out that even though people have constructed ion for that, by backward computation, like seeing what we need for the amplitude and try to find, the ion has no clear geometric meaning. I mean, it's not clear what that form is supposed to capture as far as the geometry of the moduli space is. So it is literally little brute force in the sense that you look at the IN for 5-cube theory and then you make sure that whatever poles are not poles in the 5-4, you cancel them. You cancel those poles. So yeah. So in that sense, it partially answers the question, but maybe it doesn't go up. I mean, yeah, there's still a lot remains to be done. And okay, so these are the two sort of attempts. Yeah.
Sorry, can I ask one thing? Are the scattering equations? Can you hear me?
Yeah.
So are the scattering equations? These are for n equal to 4. This is equivalent to just s plus t plus u is equals to 0, something like that, no?
Those are no. These are additional equations. So s plus t plus u equal to 0 don't know anything about the punctures, about the sigmas.
Yes. Okay.
So these are. This is the in the 4 particle case. This is the equation. One of the equations.
Is there any physical interpretation of this equation, like from the scattering amplitude point of view?
No. I mean, to my understanding, just from the physics perspective, it doesn't have any as such interpretation.
Okay.
Yeah.
Okay.
You went to an auxiliary. I mean, but I think you can say more. This really came from the Venezuelan amplitude. So this is the if you look at the string amplitude, where this delta function is replaced with some exponential and there's alpha prime there. And then if you take the limit, I think alpha prime going to infinity, you recover this this particular equation. So I think it has a natural understanding from string amplitude perspective, but within Q of t itself, I'm not sure if this has some this delta function as a physical understanding.
Okay, and capital S's are just sum of momenta. So S12 is P1 plus P2. Capital S's are those, no?
This Sij is just Pi plus, sorry, I should have said.
Yeah, Pi plus Pj. No, so
Pi plus Pj square. Yeah, sorry. Just the usual Mandelstam.
Yeah, so it looks very similar to some relation between Mandelstam variables, but you are saying it's not S plus T plus U equal to 0.
No. Those are those relations we assume. These are this is telling you that you give me some S's, can you find sigmas which satisfy this equation?
Okay.
So you are really going from the momentum to this auxiliary space. And the point is that in that auxiliary space, it is easier to classify forms or functions which give you amplitude for the theory.
Okay, thank you.
Also, in general, basics on this dimension of the piece, like 5 or 40 or 80.
No, this is very general. Yeah. Because anyway, this is so far as what Onkar was asking, that if you only have simple poles, then it's tree-level amplitude, then not much difference between dimension. We are agnostic about dimension.
What about at higher loops? What's the current status on higher loops of understanding of this formula? I mean, is there a generalization or?
Yeah, there is a generalization.
There
has been a lot of progress up to 2 loops by Montero and Geyer. And this there are multiple ways to do it. One is to think of, say, in one loop, think of the one loop amplitude as a forward scattering limit of like a tree level amplitude with 2 additional particles, so that the CHY formula we have for tree level can be used to sort of generate the integrand for the one loop. But there is also intrinsically loop formulation where the moduli space is tori or higher genus moduli spaces, which kind of goes under this amplitude the string formulation. So yeah, there is a lot of progress now, up to 2 loops as well.
Does that still rely on this holomorphic factorization of moduli space?
Yeah,
or is that
the moduli space is more complicated, of course.
Because I thought that was an obstruction to going beyond 2 loops.
Beyond 2 loops, I don't think there's been, as far as I know, there's not been much. I don't know any work beyond 2 loops, but I think up to 2 loops, I think there's a lot.
What is the obstruction?
I don't. Yeah.
Isn't it ultimate? I think ultimately this Danagi and Witten paper that the higher loop Riemann surfaces, the modular space of the higher loop Riemann surfaces don't admit holomorphically split transition functions.
Holomorphic, sorry?
Holomorphically split transition functions.
But that was for the supermoduli space, right? Or is it also for the general moduli space? Yeah. I'm not sure, but you're right that I have not seen any work for genus greater than. That's true. Okay,
thanks.
So secondly, in the case, the tree level case, at least, but just simple poles. fact that the amplitude factorizes into lower point amplitude when we so
Yeah.
that is inbuilt into like
Yeah, that is inbuilt into the geometry of the moduli space, and then the form of the form will tell you what are the residues when the two of these punctures coalesce. So actually we can discuss a lot more in CHY, but we will see reflection of this in what we will do. But here the point is that the particles going on shell is two punctures coalescing. Like one propagator going on shell is two punctures coalescing. And so and that what that means in the geometry of moduli space is that you are going to have codimensional one phase of the moduli space. And so the residue on that codimension one phase, because you're taking sigma I to say sigma I plus 1, and that residue you can show splits into two sort of two forms. Yeah.
So this ion should have that, right? When you have the residue on that one pole, the ion splits.
Yeah. Ion. Yeah. It does that. And you will see much easier why it comes out in the way you do it. Why this property comes out. So this form we will write it in terms of only the momentum space rather than going to auxiliary space.
So Alok, Young's amplitudes also come out from this.
Yeah, actually Young's it comes out very beautifully.
But there, from string theory point of view, one would have expected this to come out of some disk amplitudes. Open string.
Yes.
Rather than a closed string with a sphere.
That's an excellent point. So here, here everything we are saying we can do with a disk amplitude in the following sense that if I restrict my sigmas to be real, then I only have solutions for some restricted space of S's. But it's a trivial amplitude. So even if I have amplitude for some restricted S, I can easily analytically continue for all S because the poles, the singularities are only at the poles of the amplitude.
Okay.
So you can really do everything as a disk amplitude computation. And
Yeah.
I think without loss of generality, you can assume it gives you the correct answer.
And so you're saying these delta functions they come out of some sort of saddle point approximation of string amplitude?
Yeah. It's a bit of a weird limit where alpha prime goes to infinity as opposed to in these dual string models.
So alpha prime going to infinity.
Yes. So you take the sort of Shapiro amplitude where you have the exponent alpha prime and these are the exponents really sitting. And I think you have to take the large alpha prime limit and they get localized.
Yes. But you would have imagined to get quantum field theory, you would want.
Yeah. We can. Yeah. So these formulas don't come from. I mean, I think this is still a little bit of a puzzle. Like they come from some of the weird opposite limit.
Okay, I see.
Opposite limit. Okay, so now, sorry, I took long time for motivation. So now,
so in other words, large momentum.
Large momentum limit, yeah. So now we go to the heart of our thing. So it turns out that there is a much more there has been a lot of progress in answering this question. Not going to BCFW or not going to this auxiliary space, but simply working with the space of momenta. So yeah.
But if you take string amplitude, like proper string amplitude, let's say because and take large momentum limit or following to zero limit, you get some particular form here. And that form will give rise to something like e to the power s log s t log t, s log s plus t log t plus t log t.
Yes.
Something like that.
Yes.
But that is not tree-level amplitude of anything.
No, that is not. Yeah, so it's a tree. So the tree-level string amplitude, wouldn't it have like it to be alpha prime Sij by sigma ij, something like that? Sigma is the punctures of the. So when you evaluate it, you get S log S, T log T, etc. I'm saying don't evaluate.
Okay.
Before doing the evaluation, take alpha prime, large alpha prime limit. So this kind of gets localized onto delta. But keep the So that's how the delta functions come. And of course, these are something which is intrinsic to Q of T. These forms don't have any alpha prime anyway.
So now the integration and alpha prime is limit on.
I would suppose so. Yeah, correct.
And then you get this S log S kind of, S log S kind of.
Yeah. But I think, maybe we should discuss this because there is a work on the stringy forms by Nima and others. So,
okay.
Yeah. But the way traditionally it was understood is you take, before doing that. Okay, so now, so let me just give you an outline of what we want to discuss and then depending on time. So, Yeah, so we don't want to start with any assumption about an asymmetric grid because we just want to, the question we are asking is that, okay, I'll give you some space of momentum. For example, let's say we are assuming, because all the work I'm talking about has been done for spinless particles. We don't know. Everything I'm saying, it's not clear how to do this for particles, just spin 1 or spin 2 or something. So let me just focus on spinless particles. In case of P1 to Pn, scalar particles. The entire talk is now going to be scalar particles. But I'm not going to, as we will see that we can have masses also. So I'm not right now assuming that these particles are massless. So we have space of P1 to Pn. And we want to find like class of functions. What we want to build a kind of dictionary, a class of functions which qualify as matrix of some theory. So we don't use Lagrangian formulation, of course, or any Feynman diagrammatics or anything, but kind of want to go backwards. But so we don't really have much to start with. We only have space of momenta, except the fact that, okay, let's assume that we are in flat space so that we have to quotient it out by the point current. So this is the raw space we are going to start with, and this space is called kinematic space because there is no dynamics here. So we want to start with kinematic space, and then we want to ask this question that, okay, can I start classifying functions which give me asymmetries of some theory? So it looks like there's not much to go with, but see that there are enough structures in mathematics that can help us sort of guide towards partially answering these questions.
So that for formulation, contact diagrams, higher derivative contact diagrams, etc. also.
Yeah, very nicely actually. This Galilean theory, BBI action, they come out very nicely. I mean, in the sense that you really play with forms which are SFC weight 4, and then if you ask what Lagrangian fits, then you get very surprising Lagrangians.
Is there systematic ways to derive all of that?
Not all, I don't know, but people have, I mean, people have sort of built a large dictionary of forms which give a lot of theories. In fact, you can do a lot more. You can take, I mean, we could have a much more discussion on that. You can take, sometimes these forms look like half forms, like they look like, if n is even, then look like n by 2 form, wedge n by 2 form. So you can take n by 2 form. So you have n by 2 form, wedge n by 2 form, say, and which is giving you theory 1, amplitude theory 1. Then you have n by 2 form by n by 2 form, giving you theory 2 amplitude. Then you can ask, okay, what if you take n by 2 form of this and this wedge, and it gives you some interesting amplitude, some interesting theory also. So in really like Lego 2, you can build and see what you get. But I'm not imagining there's no been like a complete exhaustive analysis of
But all such forms will give rise to some theory, however ridiculous.
Yeah, exactly. So that's what we want to do. So we have this bare space that we want to work with, and modulo that of course we want to quotient out with point correct group. So the the translations invariance is already there in the momentum conservation, so that we are not going to worry about. So we just have to mod it out with the Lorentz group, and then naively we know that is parameterized nicely by, so such a space, let's call it Kn, is parameterized in general by Sij, which is Pi plus Pj square. Now it turns out that if you just count the number of if you just count the dimension of this kinematic space, which is the space of n momentum modulo Lorentz group, then it has a dimension which is n into n minus 3 by 2. So there is a small caveat here. The caveat is the following: that this is only true. So this dimension counting is only true if the dimension of space-time is greater than n. Because of course, if it is not, then you know that there will be complicated relationship between Mandelstam, because not all vectors are independent of each other. So, like for example, in 4 dimension, the dimension of this space is 3n minus 10. But what we are going to assume is that we are always going to work in a space where the dimension is larger than n for any n, which means effectively we are working in infinite dimension space. And this is not a problem for tree level amplitude because it's agnostic. Scalar particle tree level amplitudes are not sensitive to dimension at all of space time. So technically, when we do this, we are assuming that we are in infinite space time dimension, but it won't hurt us.
But is there a way to project it down to low dimensions?
So there is a convenient basis, which is this momentum twistor space, which kind of takes care of these complicated relations between S's. And in fact, is that space in which Hodge is transformed like polytope. But yeah, it's an interesting question to ask whether one can write these polytopes or find these polytopes in that space. But the ordinary scalar theory is not Young's theory. So right now we are just going to work with the simplest space, not momentum twistor or anything. And if you restrict dimension, you are right that it's some complicated space and one has to project, etc. And the more efficient way to do it is to go to these momentum twistors where these relations are implicitly built in them. But that has not been done.
So I mean, even for the previous question of this CHY these things, the formula is for endpoint functions.
Yeah.
Right? And there also there is an assumption about dimension being greater.
No, the CHY formula, because we never do anything like this. We just work with Sij. We never have to find like a basis and find a dimension of this. So that formula will work for.
No, but as you say, SIGs would have relations, right? I mean, the number of SIGs you get.
Yeah, but then we don't assume they're independent or anything.
They could be. So
they could be dependent. Yeah.
Dimensions, you can just put those relations and it makes sense as a S matrix of some other flow dimension.
Yeah, I'm saying that for any D, for any D1 B equal to 4, like you just have scattering equations and I give you form, but nowhere I assume that S's are not constrained. And so there the dimension information is explicitly built in that the form.
Oh.
Yeah. Like for example, if you again for scalar particles there is no such information. But if you have spinning particle, your polarization information which is feeding into here, which carries information about the dimension. Yeah. Okay, so just for so we are going to assume that this is the space that we are working with, and this space has a very convenient basis in the following sense. So if I define, so we want to find, so this is the only input we are going to use. That okay, I have this space, some kind of kinematic space, and let me first find a very convenient basis of this space, and everything kind of starts from there. So let me define variable. These are very, very simple to decide. So because so let me first define it again. So given any two I and j, where I is less than j, I'm just defining a quantity of this type. So you can see that this you immediately see two properties of this variable. One is xi plus 1 is 0, and one is x1 n is 0. Because x1 n is same as p1 plus pn minus 1 square, which by momentum conservation, which is already quotiented out, is 0. Yeah. If you assume it's a massless particle, so if you assume, so if it will be m square, mn square in general. Yeah, right. So x1n will be constrained to some constant value, and even this one, so it will be mi square. And if you have massless particles, then all these things will just be equal to 0. But basically, these are not independent. These are just some numbers. It depends on the masses of the theory. And now you can count. Okay, so what are the independent symmetric Xij's? Which you can fix where you assume I is less than j, and that will be exactly equal to this number. So these Xij's give you a good basis for your kinematic space. So let me just explain this a little bit. So they just give you example. So if I consider say n equal to 4, where we know that so we have number of Mandelstam, we have just 3 Mandelstam, S, T, and U. But they are not independent, of course, because S plus T plus U is constrained. Constant. And so we can say that the independent variables are S and T, and S, so the independent, so K4 has dimension 2, same as n into n minus 3 by 2, and the two independent variables are S and T, and as you can see, S is x13 and T is x24. And so that kind of nicely fits with the with this parameterization. But what is interesting about this parameterization is also that if I fix an ordering of particles like in the color ordered amplitudes, so if I fix some ordering.
Sorry, one question.
Yes, yes.
That in this formula vi plus vj minus 1.
Yes.
You said that condition is I less than j.
Yeah, for each pair ij or I is less than j, I define a variable xij.
Yes.
Yes.
So now you take ij as consecutive, like 2 and 3.
Yes. Yes.
And then the sum becomes only vi square.
Yes, exactly. So that's just so that variable is no longer dynamic. I mean, not independent or any.
Then how it is getting counted as Sij?
Yeah. So you have to take this and these are not independent. No.
Oh,
So these are the constraints. So these are not.
These are the constraints on SI.
Yeah, xij is symmetric and these are not independent.
So
you count it. Yeah. So that's why I give the example. The monophonic counting is not that that it exactly match with the. Yeah. And similarly, if I take n equal to 5, then you see that the dimension k5 is 3. K5 is 5-dimensional. And the number of independent xij is x13, x12 is not a variable, x13, x14, then x15 is again not an independent variable. So x24, x25, and x35. So that's the basis for the. So this is a convenient basis, and then it is more convenient for the what we were discussing before, the color ordered amplitude. So for example, if I fix say ordering of particles say 1 to 5, and let's say I was looking at say 5 cube theory, and say I have diagrams like this. I made some mistakes. 1, 2, 3. 5. So suppose I was looking at a diagram like this, then you see what are the propagators. This propagator is x13, there is p1 plus p2 square, and this propagator is x14. I mean 1 by x13, 1 by x14. So this particular channel is 1 by x13, 1 by x14. But you could do it for any. I mean, if you go to 6 point also, you will see that any channel will always be products of some xij's. And so each channel, so that's why these are called planar kinematic variables, because once you fix an ordering, then they give a very good basis for your S matrix theory. So and this space is called planar kinematic space. Coordinatized by these planar variables xij. Yes. Yeah. Okay. And now, so now this is all we have, and now let's see what we can do with this to find class of. Like, so first of all, the question is, what are the most natural functions we can find here? And now I just first sketch the algorithm and then kind of explain it through some example. So we have Kn, n into n minus 3 by 2 dimensional. And let's fix an ordering. So if you let's try to first work out this color ordered or planar amplitudes. So let's fix some ordering. So we have some n-gon like this, and we don't have, so this n-gon is just telling us that particles are ordered. There's no other information. But then once you draw this, then you see that xij is a nice sort of geometric interpretation that each, for example, x13 is a chord, x14 is a chord. So these xij's can be represented, there's no physics here, they can just be represented as chords of a polygon. And so now let me now lay down the algorithm of how we will find the S matrix.
And the chord cannot be, like, you can take the side.
Exactly. So all the non-dynamical variables are just the sides.
Constants are the same.
Yeah, the constraints are the sides. Exactly. And the algorithm is the following. So I'll just first write the algorithm and then we will see some examples. And actually, even though I'm restricting right now to tree level, because of lack of time, you can see that everything I'm saying goes through for one loop in a really remarkably similar way, except in this kinematic space, you have to find also include loop momentum. So you have to include Mandelstam, which came from P1 dot L, P2 dot L was the loop momentum. So maybe I will touch upon this in the end. So the algorithm is that one. this sort of this this chordal interpretation of this chordal representation of Xij can be used to find something, some combinatorial qualities. So again, this is nothing at all to do with physics, it's just a math reconstruction. So polytope, by polytope we only mean higher dimensional generalization of polygon. So it just any higher dimensional generalization of polygon is called polytope. So as you will see that you just give me some abstract n-gon with some chords, it can be used to generate some sort of some geometries. These are just some combinatorial geometry. They are not geometries realized anywhere. They are just something we build purely combinatorially. And these combinatorial polytopes do two things for us. They themselves will do two things for us. One, they generate differential forms in the kinematic space Kn. And these differential forms, you will see that they satisfy some. These are differential forms which satisfy, which have some inherent symmetry called projective invariance. I will explain all this maybe in a couple of minutes. Projective invariance, which really is the baby analog of dual conformal invariance in superangles. And the second thing it does is it itself. I mean, this is the important point that I don't have any other data or game to play. I just have this combinatorial polytopes which came from this pictorial representation. They generate some forms, and you can use these combinatorics to realize them in Kn. So you can actually, I mean, if I give you a polygon, suppose I give you a pentagon, and you want to realize it in a plane, you can realize it in infinitely many ways. But if you ask that, okay, if this polygon came from some combinatorial data, is there a way that I can obtain a realization which only uses the combinatorics? And so the slopes and the angles, I shouldn't use any other information to define it. And it turns out there is a way to do it, which will give us a very specific realization of this polygon. And so these polygons will be realized in Kn, and then there are these forms which are in Kn. And if you restrict the forms onto these polytopes, they will generate for us the ambiguity. So this is the overall sort of universal program, and as you see, it works for a large class of scalar field K. So in that sense, this will kind of give us a little hint of an answer that at least one class of functions which represent asymmetrics of some physical theory are forms which come from this kind of combinatorial polytopes. So maybe I first this rough idea I explain with some examples. So and then maybe after that I'll take some time to explain the kind of thing we are doing with where we can include other fields, other masses, etc. So yeah, so let me just recall. So we have Kn is just, I'm just going to write it. We have parameterized by xij's, where 1 less than or equal to I less than j less than or equal to n. And just recall that all the as mentioned that Suman mentioned that all the external x's are fixed, they are not dynamic. So now, okay, so what are the combinatorial polytopes we can easily build? So let me give you some example. So this is a construction by mathematicians. So suppose I give you, let's say that I give you one chord, x13, just one chord. So I take a, let's say that I have n equal to 5 particle case, and I give you a chord x13. And now there is an algorithm that you give me any, so what it is doing is it is breaking this polygon into a triangle and a quadrilateral. And the statement is that you give me any such dissection of a n-gon into any number of triangles, quadrilaterals, penta, whatever, and I can give you a combinatorial polytope. I mean, this is the result of mathematician. So let me explain what kind of polytope we get here. So if I start here, then the procedure is the following, that all the edges which are touching this chord, let me like label them. So this is an edge which is not adjacent to this one. So I'm not going to label it. So like it's an edge that I don't want to consider. And then now let us see that what are the, and let me now label these vertices as 1 prime, 2 prime, 3 prime, and 5 prime. Now let us see what are the chords which I can build out of this. So this 1 prime, 2 prime, 3 prime, and 5 prime. They themselves give us. Let me represent it like this. So 5 prime. So that is, I'm drawing like a dual 4-1 out of only those edges which are labeled. And I've only labeled those edges which are adjacent to the chord that I am starting with. Now you see that what are the chords that I can draw based on these edges. So I can draw 1 prime, 3 prime, which is this one. And I can draw I can draw 2 prime, 5 prime, which is this one. So this particular dissection of my 5-1 generated for me a triangulation of two possible triangulations of a 4-1, and the combinatorial polytope that we defined is a one-dimensional polytope whose vertices are these two triangulated 4-1s. Yes, I hope that this example picture is clear. That starting with 1, 3, because it's just one chord, I give you a one-dimensional polytope. What is this polytope? Where one vertex is obtained by a dissection which is 1 prime, 3 prime, and the other one is 2 prime, 5 prime, which are the only allowed ones by the rules of this game.
So you are calling the final object with just these two vertices, abstract vertices connected.
Yeah.
That's what you're calling combinatorial polytope.
Yeah, this is the combinatorial polytope. So this is
and you get that once you give me this. Once you give this pentagon.
You gave me a pentagon. You gave me a chord. And I gave you a one dimension. So number of chords, the dimension of the polytope is the number of chords we start with, internal chords we start. So because it's one, it gives me a one-dimensional polytope. And this is called a accordiahedron of dimension 1.
What's it called?
Accordiahedron, yeah. It's a it was a polytope which was discovered, I think, very recently in some sense, maybe 2016 or so. And the amazing thing is, so that there are many nice properties that we will see. But you see that if I had started with not 1, 3, but if I had started with say 2, 4, then I would get a different polytope. Clearly, right? Because I started with 2, 4, then this edge will not be labeled. So the polytope retains a memory of what dissection we started with, so we have to label it here. So again, the dimension of the polytope is the number of chords, and there is a what polytope we got dependent on what dissection we started with, so that is labeled. And except in one case where the memory is not retained of the dissection we start with, and that is the sort of, in some sense, as you see, like a master polytope which has information about amplitudes of all master scalar theories. And that is if instead of this, if I look at, so let me do play the same game, but I'm not going to look at like this partial dissection, but I'm going to look at like say a complete triangulation. So this is a complete triangulation of my 5-1, and now I have to label all the edges, right? Because nothing is left out. And then you see that, so what will this generate? This will generate, what is the polytope it will generate? It will generate a polytope, so it has all the vertices. But all possible chords are allowed now. So that is all possible triangulations of this dual is allowed. Right? Because nothing is missed. Which means I will get the polytope I will get is has 5 vertices.
We have to work with the this diagram with the prime vertices. And you could have drawn just a bunch of triangulations of the.
Exactly. In this case, you could have, yeah, but that definition wouldn't work. I will come to that. Yeah, thanks. Yeah, I will answer your question in a minute. So here Abhijit is saying that I could have just asked, okay, what are all possible triangulation of my pentagon? And I will just start writing all the, let me start from the one I started with here. Let's say this one. And then the important point is the following, that the adjacent triangulations are one where we change at most one chord. So you see, I can flip this chord and still obtain a triangulation by keeping the first one intact. And here I can do this. So each adjacent, so these are vertices of my polytope. So now remember, the dimension of polytope is the number of chords you start with. So that's 2. And each vertex is a dissection of. So I start with a triangulation. So each vertex is a triangulation. And you see that the property is that when I go from one vertex to another, I flip only one chord. And so that's the rule we follow here. Then we have so this one, then we have this one, and then here we will have
in this cyclic way, you change only one.
No, between any two adjacent, you see, if you go from
between any two adjacent, you have one common chord.
You have one common chord.
And that's why you can go out of it in general.
In general, you will go out. Yeah, exactly. So the dimension of polytope is the number of chords. So it will be first. If you did triangulation of a 6 gone, you get 3-dimensional polytope. And so each, you see that what is happening here is that, so here, this, if you look at this edge itself, forgetting the vertices, the edge is labeled by no dissection. That's so the edge is labeled by, so every time you go to a one higher dimension, you start with a vertex, which has one chord. If you go to an edge, it has no chord. So every time you go to the one higher codimension higher face of your polytope, you reduce one chord. So just to explain, like if you go from here to here, this vertex is a full triangulation, but the common edge between them is just the chord which is common to them, which is this one, which is a partial triangulation. So every, I mean, we can generalize this. Every codimension one face is obtained by removing k chords from the what we started with. Obtained by removing k chords. Yeah.
That's why you have to have a common point for these two chords. Like why can't have 1 prime 3 prime? It can't intersect this.
So say that again.
You always have 2 prime 5 prime and 2 prime 4 prime.
This one, yes.
Yes. Why you don't have 2 prime 5 prime and 1 prime 3 prime?
Oh, that's not a triangulation, right? It is. You intersect. You cannot intersect the chord. Yeah. So the point is that these are polytopes which are obtained by dissections of polygons, which no intersecting chord will.
That will create an internal.
Yeah. So this entire algorithm is that you have to look at non-intersecting chords. It is an interesting point. What will intersecting chord do? Maybe they just get some other polytope. But this entire algorithm works when you have non-intersecting chords, and yeah. And now I will just answer Abhijit's question. So Abhijit was asking that, okay, why do I have to go to this dual at all? I could just think of them as 1, 2, 3, 4, 5, and just look at all possible triangulation. And this would of course work, but it would not work here. And the reason it doesn't work here is because if I start with, and I start with, say, I started with 1, 3, I think that. If I start with 1, 3, and then I ask, okay, if I don't draw any dual, then the only property I have is that I want to look at all chords which break my pentagon into a triangle and a quadrilateral. And then I get 3 possibilities. I get these 2, and I get one more, which is 1, 4. But then it's not clear. Then I'm seemingly trying to generate something whose dimension is not the same as the number of chords I'm obtaining. And it turns out that if you go to arbitrary dimension, arbitrary n-gon, then there is no consistent definition if you start doing this at all. Right? So the non-triviality of this construction is that for any n, this rule give you like a convex closed combinatorial polytope. So that it breaks down if you just took all possible dissection, which are just the same topology as the one that you started. But except in this special case, as a question also, that in this case you see that I started with this as the reference and I got this. But of course, as you can see, you could have started with any reference and you will get the same because you are covering all possible triangulation. So this is one polytope. So again, it is one of the accordiahedron, which is dimension is same as, so in this case dimension is 2, but it doesn't rely on the reference. And so these are actually the ones that were first discovered and they are called associators. Typically just denoted with A. Okay, maybe we can put a T here for triangulation. So these are kind of the sort of the head of the family of these polytopes. They don't depend on the reference at all. They are universal. They just tell you that given any n-gon, all the triangulations of the n-gon generate for here polytopes, which don't depend on any reference or any other data like that. But as soon as you are away from triangulation, like quadrangulation or whatever, then extra data remains, like extra information.
So here you got a two-dimensional polytope which was a pentagon.
Yes.
But there could be two-dimensional polytopes which are different polygon with different sides.
Yeah, so I was just about to answer that. So now let me just give you this entire tower that So let me just. So you start with you start with the number of sides and then the your like this reference dissection. It could be triangulation or whatever, and then the polytope. And so, if you start with n equal to, of course, the smallest is n equal to 4 because there's nothing to break. And in this case, if you have n equal to 4, then you start with the 4 gone, then you can only break it into a triangulation. And so the reference dissection of triangulation and the polytope is because number of chords required is 1. Polytope is one dimensional and it's associated because it's just this, you are breaking your basic polygon into triangles. So this is a 1D associated. There's a unique polytope. So it's just this. But if you are say n equal to 5, then you can have many possibilities. You can have a triangulation. You can have a triangulation, which will give you again, we just got two-dimensional associator and a unique associator. Every associator is unique. But if you have instead of triangulation, if you have this partial triangle, if I start with partition, arbitrary partition, then I will get an accordiahedra of dimension necessarily less than 2. So that, at most 1. And they are not unique, they depend on the reference that I started with of my chords. And this kind of continues that for any n, the highest dimensional polytope, which is n minus 3 dimensional. So the associator is n minus 3 dimensional because we need n minus 3 chords to triangulate an n1. So with any n, highest dimensional polytope we get this associator and it is unique. And everything else, then it depends on if you have n minus 4 chord, you get n minus 4 polytopes. But there are many of them depending on the reference, and they are all called accordiahedron. So this is the tower that we can generate purely combinatorially. And let me just tell you what why we are going there. So as you will see that each of these polytope will give an amplitude for some scalar theory.
So how did we get n minus 3?
Because just the number of chords. Because we have the n1.
Yeah.
And we want to break it into triangles. So we need yeah.
And this is not related to the dimension of the fundamentals.
No, this is nothing to do right now with the dimension of kinematic space. Yeah, which is n into n minus 3. It's a much larger dimension.
Minus 3 also appeared there. So
Yeah. So that was. Yeah. So that is for any n greater than or equal to 4. Dimension of kinematic space is always larger than n minus 3. So what will happen is that these polytopes, as you will see, they sit inside this kinematic.
okay, I see.
Yeah, as a bit as smaller. So the picture is that inside kinematic space, these, as you will see, these polytopes are just sitting there, and we have to find them. And once we find them, then we get amplitude of some theory. Yes. N is the number of the side vertex of the polygon.
N minus is also the number of independent functions.
Yeah, that's an excellent point. So the if you take this moduli space, and that's an open set, right? Because sigmas are just, you just have sigma 1 and sigma 2 are not equal. If they're equal, you go to a four-dimensional field. But if you compactify by including the boundary, then the space you get, it's actually an associated of dimension MNC, but it's like a curvy associated, right? Not like a polytope of this type. And actually what the scattering equations are doing is giving you a map diffeomorphism between those associated and this associated.
So I think that is
I'm saying that this is the associated.
Yeah.
And okay, let me, since you asked, let me just say it for in one simple example. So as Siddharth is asking that in the CHY case also we have this n minus 3 dimensional space. So we have, let's take n equal to 4. N equal to 4. And we have sigma 1 equal to 0. Sigma 2 we can keep 3, sigma 3 1, and sigma 4 infinity. And now just for simplicity, just to explain this, let us take sigma 2 to be real. So this is related to your disk amplitude computation. So let's say that sigma 2 is real, which means sigma 2 is between, we can order it now. So sigma 2 is between 0 and 1. So it's an open space where sigma 2 is 0 is less than sigma 2 less than 1. And we can, from this we can define cross ratios. So you see that you can define two cross ratios. One is U13, which is sigma 2, and U24. Uij is sigma I minus sigma j, sigma I minus sigma. No, sorry, it's the other way around. I forget the cross ratio. Sigma I plus 1 minus sigma j, sigma I minus sigma j plus 1 by sigma I minus sigma j, sigma I plus 1 minus sigma j plus 1. So this is the usual cross ratio we define, and it turns out that you can say you have two cross ratios, I think. You have U13. We are making some mistake with the U13 will be, so see U13, so that is sigma 2 minus sigma 3, and sigma 3 is 1, so it's 1 minus sigma 2. And I think we check U24 is sigma 2. So there is two cross ratios, and you can see that both of them are between 0 and 1. Right? So U0 is less than or equal to Uij, less than or equal to 1. I mean, to begin with, that's strictly less than 1. No, sorry, less than or equal to 1. Where, and there's a constraint that U13 plus U24 is 1. So you see that this is, so we have a, we can think of these U's as some chords again. This is the U13, and then there is U24. Well, both are lying between 0 and 1. So now this is a compactification of my original moduli space. And this use is a one-dimensional space because there is a constraint here. And this itself, this is a one-dimensional associator. So the point, this space, this one-dimensional space, if you take the scattering equations, this space is mapped onto the, we will see that the polytope we realize in geometries. So there will be a direct connection in this case between the CHY formula and this this new thing that we are going to understand.
So far we haven't talked about the geometry of polytope, right?
No, not yet. Right now it's only combinatorial. We'll see when you realize it and you ask, okay, is there any connection with CHY? And there is some connection. There's a kind of direct connection between the associator and this.
No, but when you say curvy, I don't know what this means.
Yeah, I just mean that here is nothing curvy because in here when you go to n equal to 5, then you get relations which are not linear relations. It's like U13, U24 plus something equal to 1 like that. Yeah. So this is a linear polytope, but in general you will get something curved. Okay, so now let me just quickly tell you how so now we need, given this class of common polytopes, they give us two things in kinematic space. One is that they give us differential form. So there are two things that they naturally induce. So let me start with this example. So in this example, it's a one-dimensional polytope and it has labeled by 1', 3', and 2', 5'. And now let me just first give you the definition. So given this polytope, I can introduce one form. The dimension of the form is same as the dimension of the polytope. And of course, it will, as you will see, retain the memory of the reference the same way that it started with here. And let me just first define the form and see why it got introduced. So let me define a form which is dx 1', 3' by x1', 3' minus 3x 2', 5' by x2', 5'. So how did I introduce this form? This form is introduced by the following input, that it has a simple pole exactly when you touch this chord, when you intersect this chord. So in this chord, if you associate to this the variable x1', 3', and to this one x2', 5', what we are saying is that when you hit this vertex, you hit the pole of the form. When you hit this vertex, you hit this pole of the form, and you hit this vertex, you hit this pole. And the sign is coming from number of flips required to go from here to this, which is 1. So that's why there's a relative minus sign. It has nothing to do with asymmetrics right now. It is minus sign. But this is the form that we can most naturally define, which takes care of the fact that. So what is the input which is gone in here? That each vertex is a pole of the form, and the relative sign between terms is determined by the number of flips required to go from one to the other. But this form has a magic property which is true for all the forms you can write in this way. So let me write it formally as b log x1 b minus b log x 5. And this form has a property that that if I scale my xij by a local conformal transformation, to take any function of xij, not some constant xij, then you can immediately check that this remains invariant because of the minus sign. And so it has this natural scaling symmetry which is we never see in Feynman diagrams. So this is called projective invariance. So the statement is that if you ask what are the most natural class of forms you can get in kinematic space from polytopes, the most natural ones are the projective invariant form you can get, where the sign coming from the mutation guarantees that you have projectivity. And you could do this with any combinatorial polytope, right? I mean, you could do this with associated exactly the same way.
There is always an even number of terms with exactly opposite signs.
Exactly opposite sign to cancel this. Exactly. So this is the amazing thing that if you take, say, the associated term, which has 5 terms, so it looks like how can it cancel because odd number of terms. But you see when you compute it, because there are 2, it gets cancelled. So you can prove that for any of these polytope, if you follow this rule, for any n, you always get a form which has this symmetry. Yeah.
That file also.
Yeah. 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 Because it is there. Each term is a 2 form. So when you do the computation, now you will see that there are cancellations that come out very naturally. This was yeah. You can just evaluate and see that it comes. Yeah. So I hope this from the example. So let me so in the case of n equal to 5. And if you work with the associated, which is so you have 2-dimensional, we have a 2 form, and it has no memory of the reference because the associated. and then you have d log. Let me draw these primes here. They are just labeled. D log x35 minus d log x25, which so every time I do one flip, I change the sign. But now I do another flip of this, so I can change the sign again. So d log x25, which d log x24, minus d. Now I will flip this guy, so it will be d log x14, which d log x24, and now I can flip this. So 1 plus d log x14, which d log x1. Okay, so this is the two form, and you can check it. Don't look trivial, but we can check that it is like this project. Okay, so that's one part of data we have got from the polydropes, that demanding that that it's not totally, we have not got something out of nothing, of course. We are asking that at each vertex we should have a simple pole. So that's one input we have put in. And secondly, we want the form to have projectivity. And this is a very general result, which unfortunately, because lack of time, I won't be able to say that this. So you see that this, what are this? There's something special about this polytope, that it has co-boundaries of all dimensions. So here it's obvious that it's a 1D polytope, and it has a boundary which is a vertex. This is not obvious, of course, because I can have a polytope one dimension is a circle which has no boundary of 0 dimension, is not there. But what these polytopes, one amazing thing with these polytopes is that this continues throughout, that any n-dimensional polytope has boundaries of all 4 dimensions. And these kind of geometries are called positive geometries. And now the statement that for any positive geometry, such forms always exist is something mathematicians have seen, that you can always write down a form. Given you give me a positive geometry, I can give you a form which has these properties.
Look, do n equal to 6.
Yeah.
And then not consider the full triangulation, but
Yes.
triangles one part.
Yes.
And then construct this accordion.
Yes.
Accordion. That would have, how would it look like? Would it be a pentagon?
Yeah, that's a great point. Yeah.
Or a hexagon?
No, it could be a square also. I mean, we have to actually check it. So you are saying that let us consider the and you are saying let's just do this.
Yeah, I mean, I guess there are multiple choices. Now you could do it.
Yeah, you could any, but we can start with this.
Without a common point, also one can do that, right?
Yeah. Okay. Yeah,
no, but we can. We can pick any.
Yeah. So then we have this. These are our right. So then this is 1 prime, 2 prime, 3 prime, 5 prime, and 6 prime. So it's but this and then this is a triangulation. That's this one. And now we can have
Sorry, what is the rule now? When you do 2 lines, it was just to triangulate the whole thing, right?
Yeah. I'm just this is going to be one vertex. I mean, now we'll see how many vertexes we can.
No, but the way you draw I mean, why did you draw the 2 lines inside the polygon, the pentagon that you...
Oh, I'm just starting. Oh, because okay. Yeah.
The rule is to just triangulate it up.
No. The rule is to look at all chords which are allowed now. So let's see which chords are allowed. So if for example, I could have a chord which is 1 prime, 6 prime, and I can also have a chord which is 1 prime, 5 prime.
What is allowed chord mean?
Yeah. Allowed chord means that I can't have a chord which will touch. There's no chord which will go between 4.
Let's say isolate those circular things there, the primes. Okay.
Yeah, we have isolated primes.
Yeah. Then
exactly.
Then you connect everything. Right?
Then you connect everything.
Yeah.
That's it. So whatever number which is I think it will be a pentagon.
Yeah. Pentagon.
But yeah. Okay.
And then if you do the other one with no chords.
Oh, that's a bit tricky. That's a bit subtle. Yeah.
So the shape would be different.
That shape would be different. And there is one technicality which I did not tell, but now I will just say it. So. Then there is if you do it that one, you will be a little careful. I mean, these are some rules that math people gave us. So if I start with this one, as you are saying,
well, not with the prime side.
Oh, sorry. I mean, yeah.
Now we just want.
We don't have prime. We don't have prime, and now we have all the edges are labeled. But now you may think, okay, then everything is allowed.
Right.
But the point is that, okay, one rule which I should have said is that every time you draw a chord, it cannot, so I suppose I draw this chord. It cannot enter and exit cells on non-adjacent edges, which is implicit here. Like here, it is just implicit once I remove this edge, like nothing like that. But here, so this is not allowed.
Okay.
Yeah. So this chord, which is going between 1' and 5', is not allowed because it is if you look at this cell, it is entering and exiting from opposite side.
So by not allowed, you mean it won't generate an effort?
It's not part of our polytope. So we are going to generate polytopes from all chords, but this is not going to be part of that.
This is one more rule that.
Yeah. This is a one more rule means this is part of the rule, which is trivially implemented here. I was cheating a little bit. Yeah.
Basically, so far I kind of understand the logic behind this associated from, because the full triangulation means there's some tree diagram. The dual is the tree diagram, right?
Yes.
And then you can try to do that kind of thing.
Yeah.
But what is the significance of partially doing this triangulation?
Yeah, the fact that we can generate closed polytopes.
Okay.
That's the main thing. That this rule for any end.
So then that would correspond to some sort of cubic quartic vertex.
Yeah, exactly. So this will give us amplitude for a cubic part.
I see.
Yeah.
And also for the previous diagram, one time brain.
Yeah.
Let's cross this region twice. That is not.
Say the second one. No, that is fine. It has to cross and it has to enter somewhere and exit somewhere. But you see, it is entering, exiting from edges which are adjacent to each other.
Adjacent is allowed.
That's the only thing allowed.
That's the only.
Yeah. So it has to end, begin and end in the labeled edges.
Sure.
And it has to enter and exit from adjacent edges.
Okay.
So in this case, these two are rules coalesce into one. If I was cheating, but in general, you will have
Any non-adjacent entering and exiting is not.
any non-adjacent entering, exiting, even if it ends in a labeled vertex, is not allowed. If it's not entering anyway, it's not allowed. It's gone. Yeah. So if I just started with this one, then I only have labeled this. So anyway, whatever enter, there's nothing I want to see. Like those chords are not allowed. Yeah. Oh, okay. So how 15 minutes?
Yeah, sure.
Okay, so we have got one part of the data, and now let me tell you the other part, which is the how to realize this combinatorial polytopes inside KN. And what is amazing is that there is these combinatorial polytopes are related to some algebra, which are called string algebra, and then representation of the string algebra give us some concrete realization of these polytopes. So unfortunately, because of lack of time, I won't go into that. But there is a beautiful way that this string algebra construction was understood by Lima and Song and they collaborated, which is called a causal diamond approach. So it's very pretty, it's very simple to understand, and it encapsulates exactly what the mathematicians did. So let me just explain the idea. It's very, very simple. So the idea is the following. Let me go into. So we have this axis. So let me just to start with, although this approach is much more powerful. Let's just start with massless particles. So we have a single scalar particle which is only which is massless, and so all my x's satisfy xi I plus 1 equal to 0 and x1 n is 0 because all the masses are 0. And now I can let me draw some figure which will look very abstract, but it will help us find some equations which will realize these polytopes into kinematic space. So let's start. So the boundaries are dictated by 0 axis. So that means like we can start, if I start here, say that this is x3, let me draw it and it will become immediately clear. So 1, 3, x. Suppose I have n equal to 6. Okay, let me take n equal to 5. So it's like, because these x's are kind of like, these chords are null, in the sense they are like 0 length. So we are going to draw like a null lattice. So I'm going, sorry, my figures are not. So if I go down cyclically from 2, I start with a point which is x is 0. So that's on the boundary. I stop where x again becomes 0. This way. And here I'm decreasing the first entry. And now here I could go here where I will increase the second entry. Start filling in between if there is anything. So this is x3. So let me just write this x35 to x53 just for convenience. And now this x35, then I could, so x13, you see, so when I go like this, I'm increasing both by 1 unit. So if I increase by 1 unit from here, what I will get here is x14. And then I increase 1 unit, I get x25. And here x34, just write x34. And then if I increase by 1 unit, I will get x45. x45, right?
Yes. One more, sir.
Yeah, I will need one more, right?
I think that should be a little bit.
Yeah. x45 and then x 15. 5 particles. No, 6 is not there.
Oh, 5-1. Yeah, okay. Sorry.
5-1 is sorry, 5-1.
Yeah, okay. Yes.
And so now I have this. So I'm going to draw some. So this is a picture I have, and then I can. Yeah, so let me just draw something. So now I draw something where this is what is called a causal diamond. So I. Okay, so now I think the figure is very self-explanatory that each point in this diamond is like one of the labels, one of the chords, and I could go up and down infinitely, but I will just repeat my axis. So this contains all possible chords. It's like a fundamental domain, right? I mean, it's just so there is a cyclic symmetry of the whole thing because I don't get anything if I go up or down from this domain. It has all triangulations of the n equal to 5, all possible chords of the n equal to 5. And now, so if I start, so what would I mean by starting with a triangulation? Like I could start with a triangulation which is 1, 3, and 3, 5, right? So if I'm associationize something where I'm taking into account all possible triangulations, so say 1, 3, 3, 5, 2, 4, 2, 5, 1, 3, 1, 4, etc. So each pair of points label for me these dissections. And now this entire representation theory thing that math people did, that it can be very beautifully understood in this way. So we write an equation which is like Gauss's law. So we say that total charge inside this thing is 0. So what we get is x13. So let me look at this. I look at each cell separately. So I look at this block, I get x13 plus x24 minus x14 minus. So whenever I go up like this, or vertical, I use the same sign. If I flip, whenever I'm adjacent, I have to change the sign. So I flip that sign. And it's just a rule. I mean, minus x23 is, and let's say that I say that so Gauss's law will tell me that this is equal to, if there was a charge here, let me call it C, this will be equal to some C. It is some discrete Gauss law, right? And now I can do it for, there are three cells, this one, and this one. I can do it for all of them. So this one will give me x35 plus x14 minus x45 minus x13 is some C1 and another one. And now there are three equations. So you see that K5 is 5 dimensional. And this gives me 3 equations. And so I will get a 2-dimensional polytope if I have these 3 equations in a 5-dimensional space. And that 2-dimensional polytope turns out to be precisely one particular realization of a 2-dimensional association. And so let's see what that realization is. So the idea is we just put some, this is a completely arbitrary positive constant. It has no constraint whatsoever. And it won't play any role in the final answer. But you may just put it for sake of realizing the polytope. And so now with this equation, but I will just finish the in 10 minutes. So with this equation, we see that at least the associator we can realize, and it turns out that this realization is the following. So just what I'm doing is I'm taking this 5-dimensional space and I'm just putting this 3 and then just drawing the polytope. That polytope turns out to be the following. So let me give it. So I started with 1, 3 and 3, 5. So this axis I'm labeling as there are 5 axes, but we are going to when we do it like this, we can express everything in terms of x13 and x35. Of course, we can express any other basis also, but just for concreteness, which means the polytope we get can be drawn here in this plane. And then it turns out that so this equation, this phase is simply x35 equal to 0. Remember, I'm just doing massless particles. This is x13 equal to 0. This much is obvious. Then you can check that this one is x14 equal to 0. Like when you hit the boundary. This one is x24 equal to 0. And this one is x25. And so it turns out, but the amazing thing is that these are what these equations, because relative coefficients are only plus minus 1. I only have 90 degrees here, 90 degrees here, and at most 45 degrees here. Like in principle, I could have any deformation. And one of the questions we would like to ask is, what if I start deforming it? I get some polytope, and does that give me amplitude for me here? So let me first tell you what this will give. So this one we can formalize, and it's very easy now to formalize. So I just give you an example. But now we can. Yeah.
So in this n equal to 5, there was initial example of the accordion.
Yes.
One part.
Yes.
And then you should get like 4 equations. Right?
Yeah, I will just tell you how to. So how from here you can do it for any accordion. So this one, this picture nicely works for this causal diamond picture nicely works for associated. But this picture tells us something very, very simple, which is that if you started with an n-gon, any n-gon, let's say you start with triangulation and let's fix a reference triangulation, any reference triangulation. Our combinatorial polytope don't depend on the reference triangulation. But the causal diamond equation have the following compact form, that if the reference triangulation, all the chords are say T, so T correspond to all the chords 1, 3, 3n, 3, 5, 3, 6, etc. So I'm just choosing a particular reference which all originate in 3 just for illustration. Then write all the equations, write all possible equations. Sij equal to minus some positive constant, Cij, completely arbitrary positive constant for all ij which is not in Tc, where Tc is simply 2n minus 1, 2, 4. So Tc is obtained by just rotating this counterclockwise by 1 unit. So write this equation for all chords except these chords. And that this is exactly the equation the causal diamond gives. Now this formalism you can work for any accordion. Because what you are saying is that, just to take your example, if I start with, let's take a quadrangulation like this. And so we have now if you rotate it by 1 unit, you get 3, 6. So you write Sij equal to minus Cij for everything except S36. So you got a lower dimensional polytope, you get more equations, and they precisely give you a realization of that polytope. Now that itself, we don't know whether it has anything with physics, but it is something that the important thing is that this realization came from purely going from the combinatorial polytope to the string algebras, which I didn't have any time to go into. And in the case of associated, it's a very well-known algebra called type A cluster algebra. And you have to study representation of this algebra, and that representation gives you this realization you are writing. And you might have found this beautiful, simple way to understand this crazy math literature. But in the end, this is the these are the equations that you get for any accordion. So the entire realization is intrinsic to the combinatorial polytope. That's the thing that I'm going to say. And now the statement is the following. That if I start with the form, so I give you some octahedra of dimension D and with some reference, let's call the reference D. So because everything except associator depend on the reference, and I take the form which is also of dimension D, and then I restrict it onto this realization. So whatever realization I found, so let me call it realization of AC D. Sorry, I should not use D here. Let me use some dissection. Let me use Q. So I take the form and I restrict it to this, and it turns out that what I get will be some function of xij's times. Let me write, and then it will become clear what I have written. Wedge over all ij in Q dx ij. What let me, I will explain through one example, but let me first explain the formula. Then I took this form which has this minus sign, related to minus sign and all. I restrict it to the realization I find, and you can show that it turns out to be equal to some function which with whatever basis that you have started with, dx13, dx3, etc. And what this gives you turns out to be always an amplitude of some k. This quantity for any accordion. And this is let me explain why this is so. For just I give 2 examples. Then I will just I couldn't even come to the main thing that we wanted to discuss, but I just briefly summarize the thing we are currently doing. So so let me give you one example. So let's take n equal to 4. And so there the form that we have in kinematic space is d log x13 minus d log x24. If you try n equal for which you can only triangulate, there's not much choice. And the equation you get from this causal diamond is simply x13 plus x24 is a constant. And so now if I restrict, what I get is 1 by x13 plus 1 by x24 dx. And this is the color ordered amplitude, planar amplitude for 4 particles in a cubic theory with 5 cube interaction. Now if I take n equal to 5, or let's say n equal to 6, and let's take the quadrangulation. So let's take this.
So Alok, can you not get S 1 over S plus 1 over T plus 1 over U?
That you can never get here.
What is that?
Because U is a cross channel, and somehow this will always give you see, this will always give, U is something that the U channel has no interpretation in terms of these spots, you see, because if you think of it like this, that in the n equal to 4 case, each spot is dual to, now we can go to Feynman diagram because we are kind of making connections. So each spot is dual to a Feynman diagram. But if I fix an ordering, the U channel diagram is not linear. And so no chord is dual to a U channel diagram. So somehow
But the CHY formula there you can use.
no, that your CHY, even though the CHY has all the boundaries, a given integrand not give you all 3 channels.
But you get the channel by a different labeling.
Yeah, that even here you can get. So you can, but he's saying that means that, that's what I'm saying, that if you have color, then anyway these 2 channels don't mix, as we were discussing earlier, because this comes with a color factor. But if you don't have color, then you have all 3, and it is not clear how to get U channel in this. And in SR even in CHY, you don't get a single.
But it's, I'm asking it because as opposed to the disk, it is inherently spherical.
No, you are right that CHY model has all 3 boundaries. But the CHY form that gives the 5 cube amplitude, I don't think any form is known which can give all 3 channels in one. That's why you only get this color ordered amplitude. CHY. This is one of the open problems. It's not clear how these non-planar channels can be included in this positive geometry. Okay. So if I take this, just to give you one more example, if I start with this as a reference, so that the accordiahedra is, you see, 1 chord. So accordiahedra is 1 dimensional. And the reference is this one, 1, 4. And this will create a form, a planar form, which is d log x14 by x14. And you see that the only two allowed dissections for the dual are this one, which is 1 prime 4 prime, and this one, which is 3 prime 6 prime, because these two are not even labeled, so nothing else is allowed. So I will get this as a form in the kinematic space. And if I follow this equation that I wrote down, which was this Sij equal to minus Cij for all ij not in Tc, then it turns out that this one, so we restrict it, that equation is simply x14 plus x36 is constant. So this will give me, when I do that, I get something which looks very strange, but it is indeed itself an amplitude of a theory. So if I do that, I get simply 1 by x14 plus 1 by x36 dx14. And you can ask, okay, is this an amplitude of any theory? And it turns out that if you take the following theory, so consider a scalar field phi, which has two adjoint indices, let's say small a and capital A. So it has two. This is called what is called a bi-adjoint scalar field. So it has two color indices. So each amplitude has each amplitude has two sets of indices. So you have A1 to, if you have 6 particles, you have A1 to A6, you have 6 particles and A1 to A6. So you need to fix two different orderings of particles. And if you fix two different orderings which are such that 1, 2, 3, 4, 5, 6 and the other one is, I will be making some mistake here, 2, 1, 3, 5, 4, 6. Then the only common channels between these two are these channels. So an amplitude of a bi-adjoint theory where the ordering of the first is A1 to A6, but the second one is A2, A1, A6, then this amplitude is precisely this amplitude. So it is actually an amplitude of some color, amplitude of some shape.
Can you draw the amplitude? It's a quadratic one, right?
Yeah, it's a quadratic one. So for each one, this is, of course, this one is 1, 2, 3, 4, 5, 6. So that's this one. And if I replace it with 3, 4, 5, then it will be that one. So I get only two planar diagrams which are contributing. In general, of course, we need there is x2, 5 if you don't have color. But this one naturally only gives you this. Okay, so that's one thing I want to say. Now let me just in 5 minutes. Sorry, I went way over time. Let me tell you so far we have focused on the massless particle when we came to this stage of the game. And now it turns out that you can ask the following question, that if is there any positive geometry? I can just reverse the question a little bit. Is there a positive geometry which can give me amplitude of a theory, again scalar theory, but coming from a Lagrangian, which is do mu phi, what we had written earlier, do mu phi I minus, let's say, lambda 1 phi 1 cube minus lambda 2 phi 2 cube minus lambda 3 phi 1 square phi 2, all independent coupling because there is no gauge, phi 1 phi 2 square. And let's put, without loss of generality, I'll take phi 1 to be massless and phi 2 to be massive. Of course, you can take both to have unequal mass. And we can ask, okay, is there any positive geometry which gives me the answer to this? So we have a sort of partial answer to this question, that if I freeze lambda 2 and lambda 4, let's start. Suppose I look at the class of Lagrangians which have no lambda 2 and lambda 4, so only this type of coupling. Then this amplitude itself is generated from an associahedral because it's only cubic coupling, as you can see, lambda 1 phi 1 cube and lambda 3 phi 1 square phi 2. So you can imagine that everything will come from triangulation. But now there are two possible propagators in the game, phi 1 propagator and phi 2 propagator. And it turns out that the amplitude is generated from associahedra which are deformed. So they are associahedra where the shape So initially for the massless theory, this was the shape. And it turns out that I am asking it in this way. We could have asked a question actually in a reverse way. That if I start deforming, does it generate any amplitude of any theory or not? And it turns out that the deformation, I'm just being little. I'm being very schematic. Basically, it will kind of the thing will flip, and the slope with respect to the initial associator is dependent on the ratio of lambda 1 by lambda 2, which are these two couplings, or lambda 1 by lambda 3. So depending on the ratio of these two couplings, this associator shape gets deformed in such a way that you get the amplitude of this theory perturbatively. You get amplitude of this theory. And okay, just one last thing, that if you now take M2 to infinity, what happens is that if you take M2 to infinity, if M2 is not 0, then this space is not quite at 0. It is like somewhere away from 0. If you take M2 to infinity, it means you are taking this whole thing moves to infinity, and then it starts looking like a lower dimensional polytope. And that amplitude you get is the same amplitude of what if you had started with a theory which has no phi 2 because you have integrated massive field, and you have a lambda 1 phi 1 cube plus lambda 2 by m phi 1 4 interaction, where you are taking m to infinity, lambda 2 to infinity, so that the ratio remains constant. So as we know that this is coming from some upper diameter, and that upper diameter is precisely the polytope you get if you started with this deformed thing and take m to infinity. So the two things nicely match in the process. So right now we are trying to see if we can switch on all the couplings and if there are any polytopes with this. Sorry, I went way over time.
So the choice of these CIJs depend on mass and coupling.
No, actually C's are completely arbitrary. The only condition is that positive. They don't play any role in the final amplitude at all. So the coupling dependence actually comes on. It only comes when the equations start getting different. So remember the initial equations were like x13 plus x24 is some constant, for example. So it turns out that this equation can deform to lambda 3 by lambda 1 x13 plus x24. And in some sense you are right that this there are some m square floating around which will get absorbed here. So you are absolutely correct. In that sense, the this constant, we can look at it two ways, that is c plus m square, the whole thing is a constant. But at the end of the day, for any c and any m,
it's basically scaling.
What is important is this thing. That this is kind of telling us what is it called, where it intersects, basically the thing. But the important part is the slope that comes from the ratio of the two. And in fact, we can ask if one of the coupling was I just run out of time. We can ask what happens if one of the coupling is negative. Then it turns out that the polytope loses its convexity. And so, the fact that the Sikh theories with negative coupling, which have the superluminal propagation, we don't have any concrete proof, only some very simple example where they seem to be tied to concave on lack of.
These are the signature of causality also.
But it is at this very speculative state. It's signature of causality from the effective field state perspective. Sorry, I took too much time, but I stop here.
May I ask a question?
Yeah, please.
Hi, Alok. So I wanted to ask, for massive particle with spin, what is the hurdle exactly? Is it not clear whether there is a positive geometry there? Or?
No, for single massive particle, there's absolutely no problem. Sorry, I didn't say it explicitly. So everything we were doing up to a point was agnostic, as you remember. Like we just took x1 n to be, it was mn square, but we took mn to be 0 at some point, but it was not necessary. So if you have a single mass, then the whole thing that happens is that this polytope just shifts, like rigidly shifts, because basically the pole should be at x3 phi equal to m square and x13 equal to m square. So there's absolutely no problem with a single mass. Is that what you're asking, Saurabh?
No, I'm asking with spin, massive particle with spin.
Spin. Oh, spin, even without mass, I think we don't have any, I mean, if you have spin, then we can first of all not work in the momentum space because we need polarization. So we can work in spinor helicity space, but as far as I know, there is no polytope known for Young mills, for example. Like there's no, we don't know any polytope which does all these things that we discussed.
I see. Okay.
Yeah, I don't know the hurdle means, like, yeah, I don't know exactly what the obstruction is, but yeah, no one has found it.
So the polarization cannot be added.
So yeah, I mean, we can go to the spinor helicity where it's just,
But that is only for 4-dimensional sum.
yeah, that's only for
That's what
Yeah.
I was.
yeah. So here I don't know. I mean, what is I in some sense ironical is that
Getting a 1 plus minus and then 2 minus. All those are spin functions, right?
yes.
And then I thought that maybe it is just for d is equal to.
No, you are right. The spinor helicity is only d equal to 4.
Yeah.
But the at least in that space, everything is in the spinor helicity space.
Yeah.
So at least in that case, there may be some hope of finding a polytope for 4D amplitude. But in general, I don't know how to even start because we'll have to add extra polarization data here.
Yes.
And yeah. Also, the point is once you have spin 1, then the residues are not 1 or 0 or right. I mean, the residues have some dynamical information, momentum information. So these forms should not be so simple with simple poles with plus or minus 9, or with some residues which are just this coupling dependent. Right? It should be more complicated. So I don't think one knows how to. Yeah.
Sorry, wasn't initially this discussion about n equal to force?
Yeah, that's a strange thing that for some amplitude hedron, n equal for super Young mills, you can go to this momentum crystal space and you can write these forms. I mean, initially people wrote forms. People thought, I mean, the whole story is that for amplitude, people realized that it is a differential form which is dual conformal invariance. There was no polytope. Then people realized, oh, this is canonical. This form is actually intrinsically tied to some polytope. But as soon as you drop supersymmetry, it's not clear how.
So when you for the super Young mills case, you know the polytope.
You know the polytope. Yeah, and that's actually, it much more than, I mean, the information is, it, it's an exact form to all loop orders. So it's not some tree level or something. So it has a, yeah, it potentially also has a lot of non-perturbative information in the thing. Here we don't have anything like that. If much we can do. So everything I said here, the entire program will go through if you cleverly define one loop kinematic space. Where you have P1.L, P2.L, and it's very nice that mathematicians have looked at these triangulations of, so if you have a loop, so in the tree level case, we have this, our diagrams are dual to simple polygons with triangulation. If you have a loop, then what you need is like a, naively would think you need like a hole in the polygon. And then people have studied, mathematicians have studied triangulations of these quantities. And it turns out that the entire program can be used to define amplitude is exactly the same way. The integrands of one loop in exactly the same way. Your projective form, and this was initially these kind of polytopes were done where you triangulate it, but it was not through this process. I found some polytopes which give us integrand for 5/4 or generic loop integrand for this theory. But those polytopes also, because of physics motivation, we found them. I mean, it's not clear if mathematics interested initially in those polytopes. So, yeah.
So you guys know the one loop for all 5 again.
One loop for all 5 and for massless particles or a single mass scalar field. We know the integrand here. I mean, we can write the integrand, we know the procedure. We explicitly wrote it only for 5⁴. So, yeah. But even this deformation, we may have only worked out some example, but this entire deformation to be also the loop integrand goes through very nicely. The same deformation applies to the polytope we have there and gives us the integrand for the one loop case.
So this is a slightly general question, but most of this discussion one has this for loops, one gets some integrand, right?
Yeah, you want the integrand.
Is there anything nice about the integrand?
Yeah, I mean so again for the super Young mills, the amplitude run gives us the integral. So it's the with these PDS answers where you just abstract out the IR divergence. So you have IR finite amplitude, and that has the geometric interpretation volume of this amplitude return. But for the non-supersymmetric case, yeah, these polytopes, I think for the integral, Nima and Sebastian have some recent work now, where they are defining these polytopes in the Schwinger parameter space. So not these polytopes, nothing to do with that. But so again, that's in the integrals have some positive geometry, this kind of interpretation, but these are polytopes in the Schwinger parameter space. And they are Newton polytopes. They are not this. I mean, they are different polytopes. They are not polytopes coming from combinatorics of chords.
Okay.
Yeah, but they are positive geometries in this sense that they have codimension, all codimension, faces of all codimension.
So just another one kind of question, general question. So in order to get some clustering kind of amplitudes,
Yeah.
you instead of the starting point being this triangulation of something, but one consider like a triangulation of a sphere itself, other than and then some spherical object, basically object of this kind, and then cut it.
You are saying for the string amplitude
In order to get STU.
Oh, STU, yeah. So, I've often wondered about designing the fact that the modular space, which has all three boundaries, is complex, right? It's the complex sigmas, which has all three. So, if I take the real disk amplitude, it has only two boundaries, right? Because if I take n equal to 4 case, so I have sigma 1 is 0. It can only coalesce with 0, or it cannot coalesce with infinity. So, it is only 2. But so I have to be complex sigma, which means I have to somehow look at some complex polytopes or something. Yeah. But the confusing part is even in C2 also the boundary are present, the form don't give you contribution of all poles. So yeah, I must say that there are these just asking analysis. So that it's not true that we can get any non-planar chance information. We can get of this class of amplitude. So if I to consider the following class of cubic amplitudes, where I fix the first and the last leg, and here I allow all possible commutation. You can ask this information can I obtain from a polytope, and that polytope is a polytope which doesn't come from this kind of chords, etc. It's called permuta heat. So there is some polytope you can define, the mathematician define, and you follow the same game again. You can realize it in kinematic space, your form, it will give you a projective form, and it will give you amplitude of this channel. But you see that this one has still missing the U channel. Because if I took 4 points, then I have 1, 4 I fixed, then I missed the U channel. So all the U channel information is hidden.
Planar things, right?
Yeah, it's only planar. Even though I mean this is not planar strictly in the sense that, but it has the U is missed.
I see. Thanks.
Are there other questions? Okay, let's thank Alok again.
Thank you.